For the week 6 lab, we start off by creating a confidence interval for the sleep variable from our database. So the sleep variable measured how many hours of sleep the people got the night before, and a confidence interval is going to let us guess or estimate the average for the entire population. So in our database, and this is a different database than the one you'll use, but we have data from 35 people. We have a sample of data. And so we can find the average of that sample, but our confidence interval is going to let us estimate the average for the entire population of everybody. And we create our confidence interval using mathematics and statistics, so it's very precise and it's not a guess or an estimate in the sense that we're just hoping it's correct. We're going to be able to say with 95% confidence that the interval of numbers we create here actually really does contain the true population average for the hours of sleep. So question 1, we're going to find a 95% confidence interval, and the steps are laid out very well here. I'm going to go through them in Excel. So we need to focus on the sleep data here from our 35 people in our sample. And we want to first start off by getting the average from our sample, the mean from our sample. This value is going to be right smack dab in the very middle of our confidence interval. Is what we would call a point estimate or a single value estimate for what the population mean is. So after finding the mean, we also need to find the maximum error, and Excel can do that for us. And the maximum error tells us how wide our confidence interval should be. We're going to subtract it from the mean to get the lower bound, add it to the mean to get the upper bound. So in order to get that maximum error, we use a couple more formulas. We need the standard deviation of our sample. So standard deviation dot S, because we have sample data here. Don't use dot P because that's if you have the entire population of data. But you get your standard deviation of your sample, and then Excel has a nice built-in formula that will tell you what that maximum error is. And so you need to type in what your confidence level is. And if we're 95% confident that our interval will contain the population mean, it means there's a 5% chance that it won't. So we enter in the percent that it won't contain the population mean here as our first argument. And then the second argument is the standard deviation. And then the third thing you need to type in is the sample size, which there was 35 pieces of data. So this is how, in a sense, how wide our interval needs to be out from our sample mean, our point estimate in the middle. So for your confidence interval, you put that point estimate in the middle. That's our sample mean. And then we just add that maximum error. We add it to the value in the middle, the point estimate, to get the upper bound, and subtract it from our sample mean, our point estimate, and that gives us the lower bound. And so these two values here, our lower bound and our upper bound, that is our confidence interval. We are 95% confident that the population mean for hours of sleep, the population mean is somewhere in between these two numbers. And what we mean by 95% confident is that if we did this same process 100 times, which means we would gather 100 different samples of size 35. We're doing the whole process over 100 times. Out of those 100 samples we gathered, we do this whole process of building the confidence interval. 95 out of those 100 will contain the real population mean somewhere in between the lower and upper bound. We don't know what that population mean is, but 95 of the intervals will have it somewhere within the lower and upper bound. The other 5% will not contain the population mean. It would either the population mean will either be below the lower bound or above the upper bound, but it's somehow outside that range. And it's important to understand that we don't know for sure whether this confidence interval contains the population mean or not, but we're 95% confident that it does, because 95% of the time, if we do this process and do the math correctly like we did here, the population mean is within our confidence interval. For number 2, we're doing pretty much the same thing, but now with a 99% level of confidence. So if we would repeat this process 100 times, 99 out of 100 of the intervals would contain the population mean. And so we already have our point estimate from our sample. That's still going to be right in the very middle of our confidence interval. Our standard deviation is not changing. The only thing we need to do is find our new maximum error here, where for 99%, that means there's a 1% chance that our interval does not contain the mean. So enter the 0.01 there, and then the same standard deviation, the same sample size, so we get this value. And so add that to your point estimate, your sample mean, to get your upper bound, subtract it from the sample mean to get the lower bound, and now we're 99% confident that the population mean is somewhere in between the lower bound there and the upper bound. So using the same exact sample, how did we get more confident? Well, you can see from our numbers here that an increase in confidence is resulting in our interval being wider. We have a lower bound and a larger upper bound, so we're less precise here in our guess of what the population mean is, because we have a wider interval that we're saying we're confident the mean lies between. So it's less precise, it's wider, but it also gives us a higher level of confidence that the mean really is between those two numbers. And what I was just talking about there, comparing the two intervals, that's what you want to do in question 3. For the rest of the lab, we'll be looking at the drive variable, which is the average amount of time it takes a person to drive into school. And we're told to assume that this variable is normally distributed, and we're going to start off by finding the average and the standard deviation for our distribution. And we're just going to use the mean and standard deviation from this sample. And so just do the average formula in Excel to get the mean, and do the standard deviation.s, because it is a sample, to get the standard deviation for our distribution here. And so in question 4, we want to list that mean and standard deviation, and then we're going to find the predicted percentage that drive less than 40 miles into school. And then we'll end up by finding the actual percentage from our sample that drive less than 40 miles. So the predicted percentage, we can use the fact that we have a normal distribution to find the percent of data that would be at 40 or even further to the left, further less than 40. And so the formula in Excel is norm.dist, and you put the value you're trying to find the probability for, and then you type in the mean and then the standard deviation, and we always type in true here, and what that gives us back is the probability of a data value being at 40 or even further left, further less than 40. In picture form, what we're finding here, we have a normal distribution with our mean. It's always right in the middle, and we're asking what percentage of the distribution of people driving to school here would have a commute of 40 minutes or less. And so we're finding what percentage, what proportion of the population lies at 40 minutes or less further to the left in our distribution. And the answer we get back is, right around 33%. And now to find the actual percentage from our sample, we're just going to look at the data and count how many people have a commute of 40 miles or less. So it looks like this data is already sorted for the drive. If not, you can select it all and then go to data, sort, and you'll want to sort the drive column based on the values. And you can do smallest to largest or largest to smallest, whatever you want. But then once it's sorted, we can go in here and count. So so problem said less than 40, so we don't want to include the 40, but it looks like then we have a total of 14 numbers less than 40, because our first row here is the header. So if it goes down to 15, that means there's 14 numbers. So that is 14 out of 35 that have a commute of less than 40. So 14 divided by 35 gives us 0.4, or 40% is our actual result. And so we have our actual percentage and the predicted percentage, and you can compare those two. And then for number 5, well, what percentage of the data would we predict would be between 40 and 70? And then also, would we predict to be more than 70? And for both of those, we're going to do the predicted data using our formula in Excel, and then look at the actual data and see what that percentage is. And again, compare the two. The needed formulas are listed here. I'll demonstrate again in Excel. For finding the percentage that we predict to be in between 70 and 40, we use the same formula twice. First time was 70, mean, standard deviation, true, and then we subtract away with 40, and the same mean, same standard deviation, and true. And it gives us then the percentage that's in between those two values. And an illustration, a visual, really helps show why that subtraction works. When we do that formula in Excel, we first do it with 70, and Excel gives us back the percentage, the probability that a random data value will be less than 70. So it includes all of everything less than 70, and it gives us that probability back. And then if we want to know the probability of being in between 40 and 70, we need to subtract away this part that is less than 40. And so if we do the subtraction then with that same formula in Excel, it calculates the probability of less than 40, and that's what we're subtracting away. So all we're left with then is the probability of being in between 40 and 70. So everything less than 70, and then subtract away the probability of less than 40. To find the probability of being greater than a value in our normal distribution, we will do 1 minus, and then that same formula. And for this lab, we're looking at the probability of being greater than 70. And so again, enter the data value, the mean, the standard deviation, and true. But do 1 minus that, and let's look at the illustration. Using that formula in Excel always gives the left-hand probability of being less than it. So when we type it in, Excel's giving us back this probability. And so all that's left is this little tail over here of being greater than 70, and that's what we actually are trying to figure out. And so we need to recall that probability, the probability of everything under the curve adds up to 100%, or 1 if we're looking at it as a decimal. So this part to the left and this part to the right, that is everything. So together they will add up to 1, or 100%. And so whatever this value to the left is, if we do 1 minus that, it's the value that's to the right. And that's what we're trying to figure out, the probability of being greater than 70 in the distribution. And then after finding those theoretical predictions, go back and look at your data, and you're going to count how many are greater than 70 for the actual value. And then we also wanted to know how many were in between 70 and 40. So you would count the ones that are strictly in between 70 and 40 for the actual value, for that actual percentage. And then talk briefly about just the comparison between these predicted percentages and actual percentages, which one was larger, which one was smaller. And then why is there a difference in between the predicted percentage and the actual percentage? And you can talk about how these predicted percentages are giving us the probability we're going to get a certain outcome, but probability can't dictate or cause the actual outcome. So when we gather a sample, sometimes it's really close to the predicted probability, and sometimes it's a little further away and larger or smaller, because probability doesn't dictate what's actually going to happen. It just talks about what's the most likely outcome to occur. And also, tying in with that, these predicted percentages, um, the larger sample we have, we would expect our actual percentages to start getting closer and closer to the predicted percentages as our sample grows in size. That's the law of large numbers. Our actual outcomes that we're noticing in real life will be closer and closer to the predictions when we have larger and larger samples.